a heavy atomic nucleus with the release of radiation and heat. And what causes nuclei, that's the plural of nucleus, to disintegrate during radioactivity is the unequal number, the unbalanced nature of proton and neutron. For any nucleus to be able to be stable, it must have a well-balanced neutron to proton ratio. So the correct answer here is option C, a balanced neutron to proton ratio. Whenever the neutron to proton ratio is balanced, is about 1.1, provided it is not more than 1.5. Any nucleus whose neutron to proton ratio is more than 1.5 is not going to be stable. And if you say a nucleus is not stable, what does it mean? It means it is radioactive. It will now become unstable and become radioactive. So a balanced nucleus is a nucleus that has a balanced neutron to proton ratio. The next slide. Okay, which of the following is not a use of radioisotopes? Option A, detecting leaks. Option B, diagnosing disease. Option C, generating electricity. And option D, improving the taste of food. Now, we have different and various radioisotopes. Carbon 14 is a radioisotope. It is used for carbon dating. Cobalt 60 is a radioisotope. It is used in treating cancer, and also it is used in industrial radiography in detecting faults in metals and castings. And we also have iodine 131 is a radioactive isotope in diagnosing thyroid cancer. Not only that, we have a lot of them. We have phosphorus 32 in treating blood cancer, also leukemia. And not only that, we have a lot of radioisotopes used in generating electricity. And the vast countries of the world, they don't generate their electricity from water like we do here in Nigeria. They generate their electricity from radioactivity, from radioactive materials. So radioactive material can be used for a lot of things. They can use to detect leak in pipes. They can use it to generate electricity. We can use it to diagnose diseases. But we cannot use radioactive isotope to improve the taste of food. However, we can use radioisotope to preserve food. There's a difference between food preservation and improving the taste of food. Radioactive material, radioisotope cannot be used to improve the taste of food, but it can be used to preserve the food so that the food does not become spoiled. So the correct answer here is option D. We cannot use radioactive isotope to improve the taste of food. The next slide. Okay, the anion that gives white precipitate with silver tricosinated 5. The source in ammonia is dash. Now, chloride ion, option A, bromine ion, iodide ion, and nitrate ion. Now, when we are testing for chloride, we do three things. Number one, we are going to add silver tricosinated 5 to that particular solution we want to test for chloride. After that, we add dilute HNO3. And finally, we add aqueous ammonia. When HNO3 is added, a white precipitate is going to be formed. And when we add excess of aqueous ammonia, if chloride ion is present, the white precipitate dissolves to give a clear solution. So the correct answer here is chloride ion. Let's go back to that slide 3. Okay, now you can also test for iodide ion, you can test for bromine ion, you can test for nitrate ion. How do you do that? If you want to test for iodide ion, you can use the same method. You can add HNO3 to that particular substance. After that, you add dilute HNO3, and then a pale yellow precipitate will be formed in the case of a bromine ion. That pale yellow precipitate will be soluble in excess aqueous ammonia. But when you are testing for iodide ion, it's going to give a deep yellow precipitate when you add AgNO3 and HNO3 to it. That particular deep yellow precipitate will be insoluble in excess aqueous ammonia. So, if you want to test for chloride ion, white precipitate will be formed and the precipitate will be soluble in excess aqueous ammonia. If you are testing for bromine ion, a slight, or maybe you should call it pale yellow precipitate or slight yellow precipitate will be formed, and that precipitate will also be soluble in excess aqueous ammonia. But if it is iodide ion, it's going to give a deep yellow precipitate. But this time around, that yellow precipitate will be insoluble in aqueous ammonia. And if you want to test for triosonitrate 5 ion, what do we use? Brown ring test. So it is brown ring test that is used to test for NO3 ion. So the ion that will give a positive result during brown ring test is triosonitrate 5 ion. The next slide. Okay, which of the following turns starch iodide paper blue black? The only gas that will turn a starch iodide paper blue black is chlorine gas. Starch iodide paper is potassium iodide. When chlorine is added to potassium iodide, what happens? The chlorine will displace the iodine, and the iodine will now combine with starch. And what's the color change? When iodine is added to starch, it turns dark blue or blue black. So, if you look at the 4 gases, the only one that will turn a starch iodide paper blue black or will turn a potassium iodide paper blue black is chlorine gas. If you look at ammonia, ammonia can be tested for in 2 ways. Maybe from the smell. Ammonia has a characteristic pungent smell. And apart from that, we can actually test for ammonia by using hydrochloric acid. Ammonia will form a dense white film of ammonium chloride with hydrogen chloride. That's actually the major test for ammonia. Ammonia is the only gas that forms a dense white film of ammonium chloride, NH4Cl, with hydrochloric acid. And if you want to test for nitrogen 2 gas, which is NO, we can test also for it by making use of the brown ring test. As a matter of fact, it's a question in JAM. The only gas or the oxide of nitrogen that can be used to demonstrate brown ring test is nitrogen 2 oxide gas. And if we're talking about SO2, we can test for SO2 either by the smell, because SO2 has a characteristic choking smell like burning matches. And not only that, we can test for SO2 by adding concentrated acid to any salt that contains triisosulfate 4 ion. So these are the ways you can test for the remainder of the gases. But the only gas here that can turn a starch iodide paper or potassium iodide paper dark blue or blue black is chlorine gas. The next slide. Yeah. Say that again. Chlorine gas is not a reducing agent. Chlorine gas is an oxidizing agent. Yes, chlorine gas is an oxidizing agent, not a reducing agent. Yes, both of them bleach, but they bleach differently. Chlorine bleaches by oxidation, sulfur oxide bleaches by reduction. The only similarity between the bleaching action of chlorine and sulfur oxide is both of them require water for their bleaching action, but they bleach differently. You can use chlorine to bleach all this material that can withstand harshness, but you can use sulfur oxide to bleach material that are actually very fragile and delicate. But don't make the mistake. SO2 is a reducing agent, although it can function also as an oxidizing agent, but chlorine is always an oxidizing agent. Chlorine is never a reducing agent. anion that evolves gas with dilute acid but gives white precipitate with barium chloride is dash. If you look at this, the correct answer is option B. Now, option B is triisocarbonate 4-ion. When carbonate reacts with acid, what is the gas given off? Carbon 4 oxide gas. That's what they meant by saying that the anion that evolves gas with dilute acid, when any dilute acid, be it ACl, H2SO4, is added to any carbonate, the CO2 gas will be given off. And when barium carbonate is added to carbonate ion, it's going to form BaCO3, which is a white precipitate. So the correct answer here is B. You shouldn't even spend more than a few seconds here. Immediately you see that the anion that evolves gas with dilute acid, it is only carbonate ion that will evolve gas with dilute acid. Sulfate ion does not evolve any gas with dilute acid. Chloride ion does not evolve gas with dilute acid. And then nitrate ion will only evolve gases with concentrated acid, not dilute acid. The correct answer here is carbonate ion, option B. Okay, number 6, a gas that turns potassium dichromate paper green is dash. Now, potassium dichromate is also called potassium heptaoxodichromate 6. That's K2Cr2O7. We know that acidified K2Cr2O7, potassium dichromate is an oxidizing agent. And whenever a reducing agent is added to an oxidizing agent, the color changes. Now, the original color of potassium dichromate is orange.